Predicted Topics for Paper 2 OCR A-Level Chemistry Exam 2024. What to expect in your exam? There will be several questions on the use of analytical techniques like the mass spectrometry, NMR, and IR, and they could either ask you to identify the structure or to differentiate which spectrum is for what compound. To plan an experiment for stances, this is a definite question in your exam. Reaction schemes with missing reagents and compounds, new reactions that you've never seen before, and you would need to simulate this reaction to find the product on the different reactant, and then reaction mechanisms. And finally, isomerism. So the first topic is the analytical technique. So the mass spectrometry, it's used to identify the molecular ion peak for the molecular mass. So the molecular ion peak is the peak at the far right with the highest value. This is going to give you information about the molecular mass of your compound. Then you can notice the fragmentation pattern and the values of the fragments, the m over the value of the fragments to identify the structure. The most prominent one is the presence of a fragment like M over Z29, which indicates the presence of an ethyl group. For example, you have these two compounds which are functional group isomers. They have the same molecular formula, but they have different functional group. Both of them have the exact same molecular mass. However, in the mass fragmentation for the aldehyde, you're going to have this ethyl fragment. So you're going to have a fragment with 29. But for this one, the ketone, there's no ethyl, it's just two methyl. So you will not going to have this 29. So you can differentiate when the spectrum which have the 29 fragment is going to be for the aldehyde. Sometimes as well, they can go a bit more deeper. So these are two compounds as well, two isomers. Both of them are ketones. If you look at the mass spectrum for both of them, you're going to find the main difference here is in this peak, which is 71. The peak 71 comes from the loss of an ethyl fragment or a loss of 29. That means only the compound that can lose an ethyl fragment is going to be that compound. So you can notice that this one can lose an ethyl fragment. This one cannot lose an ethyl fragment because there is no ethyl here that can be lost as a fragment. IR, the most prominent peaks in the IR which you can easily use and identify even without looking at your data booklet is this peak here, which is a strong and a sharp peak at around 1700. This is for a carbonyl stretching vibration. So a carbonyl group, this could be from aldehydes, ketones, acids, or any of the acid derivatives like amides or esters or even acid anhydride. And the second one is this peak here, this broad peak at around 3400, and this is for alcoholic OH group. Remember that the fingerprint region will always be different if you do any small change in your compound because the fingerprint region, this region at the beginning here at the far right, this is used to identify the structure where you can compare it to data sheet or you can compare it to the data bank to identify the structure of your compound. Carbon-13 NMR, when you look at the spectrum of carbon-13, the first thing you can identify is the number of chemically non-equivalent carbons. So here you have, for example, in this spectrum, you have 4 different chemically non-equivalent carbon. You can also easily differentiate between aldehydes and ketones by looking at the different peaks. So usually the carbonyl carbon comes in the higher range between 200 and 220 parts per million, while the carbonyl group from acids and esters comes a little bit to the right, so between 160 185. Also, the carbon which is next to an oxygen or next to a chlorine can easily be spotted because it's a bit higher, so it's around 70 or 75. So you can easily spot these types of carbons. And then the carbon next to a carbon atom is usually at the far right. No, most of the time, it's going to be somewhere less than 20. For the proton NMR, you need to look at several things. First one is you can determine the number of chemically non-equivalent protons. This is the according to the number of the signals you see or the number of peaks. So here in this table, for example, we have 4 different signals, and that means we have 4 different non-chemically equivalent protons. And then the integration value will give you the number of protons that give you that particular signal. Sometimes they don't even give you the integration and you have to find it out yourself. Sometimes they give it to you as a ratio. For example, if they give it to you as 0 0.6, 0 0.6, and 0 0.9, it's going to be like 2, 2, 3 protons. So you can always work with the ratio to find out how many protons are there. Remember that the chemical shift will, you're going to use your data sheet or the data sheet or the data booklet to determine the most probable chemical environment. So if it's at the far right, less than 2, it's going to be carbon next to a carbon, hydrogen next to a carbon. If it's a bit in the middle, around 3.5, 4.5, this is probably going to be carbon next to an oxygen. And if it's something like around 2.5, it's a carbon hydrogen next to a carbon with a double bond oxygen. And then if it's a bit further away, maybe it's an aromatic where you can see it in the range of 6.5 until 8.5. Remember that the splitting gives you information about how many hydrogens are there on the adjacent carbon. So if the splitting is singlet, that means no adjacent hydrogens, or maybe it's next to an OH, or maybe it's an OH. That will depend on where the position of the signal. If it's a doublet, that means it has only one adjacent hydrogen. If it's a triplet, then there are 2 adjacent hydrogen. If it's quartet, it's 3 adjacent hydrogen. So the count will always be n plus 1. Even if you don't figure out the correct final structure of your compound, you don't need to worry too much because your interpretation will give you most of the marks. So just follow the interpretation, how to interpret your spectrum, and then you can get at least most of the mark even if you don't get to the final structure correctly. Topic 2 is the reaction mechanism. So rule of thumb here is that curly arrows go from electrons to electron deficient atom or towards a single bond to make a double bond. In the exam, you're going to have several reaction mechanisms. You're going to have questions with missing arrows. You're going to have organic synthesis questions, a whole mechanism question, and plan an experiment. So remember that when a bond is added, another has to be broken unless you are making a positively charged oxygen or nitrogen, especially nitrogen because it can be a quaternary salt. But other than this, everything, once a bond is formed, another has to be broken. So before we go into the reaction mechanism, just remember the difference between nucleophiles and electrophiles. So a bond is formed when electrons move from a nucleophile to an electrophile. So nucleophiles could be anything with a lone pair of electrons, like ammonia, like an amine, like water, like an alcohol amine, could be primary, secondary, or tertiary. You could also have nucleophiles which have negative charge, like hydroxide ion, like bromide, like an OH, like bromide, or even like a hydride, which is a hydrogen with a negative charge, like we will see in the reduction of carbonyl compounds. You could have a nucleophile also with a carbon-carbon double bond. So alkenes will act as nucleophiles. So all of these, as you can see, the electrons will move and will be given to an electrophile. Electrophiles will have a positive charge or they're going to be electron deficient. So like a hydrogen, which has a positive charge like a proton, And then if you have a double bond to an electronegative element, so if you have a double bond like here, like the carbonyl group, then the carbon, because it's next to a more electronegative element, then this is going to be electron deficient and it can act as an electrophile. Also, if you have a single bond next to an electronegative element like hydrogen chloride, this hydrogen will act as an electrophile as well. So the as we said, when one bond is formed, another has to be broken. So now we have this ammonia as your nucleophile attacking the hydrogen, which is your electrophile. Then this single bond has to be broken, and the electrons have to move towards the chlorine. So the most important reaction mechanism, I will go quickly through them. I'm not going to go into too much details into them, but just to remind you because several reactions will come into your exam. So first one is the radical chain reaction. This is for alkanes where they are chlorinated. This is photochemical chlorination of alkane. There are three steps of this reaction. In this reaction, the initiation, propagation, and termination. Initiation, when the chlorine free radicals are formed, and propagation when the free radical formed start to attack your alkane to make more free radicals. So every time there are a new free radical formed, and then termination at the end when the free radicals that have been formed react together to give you the final products. This reaction is very dirty. You're going to end up with so many different products, so it's not favorable reaction. CFC and the ozone layer, this is one of the questions that are expected in your exam, and it's very common. So any chlorofluorocarbons, whatever they are, as long as they have one chlorine atom, then they can generate the chlorine free radical under the effect of the UV light. The chlorine free radical is the one that is going to attack the ozone. This is to break the ozone to give oxygen, and another free radical which reacts with the ozone again to give oxygen and chlorine again free radical. As you can see, the chlorine free radical has been regenerated, so it simply acts as a catalyst. Nucleophilic substitution reactions, from the name, this is substitution, and the attacking species is going to be a nucleophile. So a nucleophile, anything that has either a lone pair of electron or it could have a negative charge. You're gonna see this type of reaction when you react alkyl halides with nucleophiles. So alkyl halides like methyl chloride, ethyl bromide, or whatever. So as long as you have a halide here and you have a nucleophile, the mechanism of the reaction is so simple. So you have the lone pair of electrons or the negative charge. The electrons will go to the partially positive carbon, while the bond between the halides and the carbon breaks. So whatever your nucleophile, it's going to be exactly the same mechanism. You just need to know the conditions for some of the reaction, like with cyanide, you just reflux in presence of ethanolic sodium cyanide or potassium cyanide. In case of ammonia, you also reflux with excess of ammonia and use ethanolic solution or ethanolic ammonia. Remember that the product here with ammonia is not going to be a pure primary amine, because the primary amine formed is again going to act as a nucleophile. So it's going to re-attack the alkyl halide, and then that will give you secondary, and then you also can get the tertiary and the quaternary ammonium salt. The elimination reactions, so any elimination reaction, you are removing two groups or two atoms onto adjacent carbons to make a double bond. So the first one is the synthesis of alkanes from halogen alkanes. In this reaction, you are heating with ethanolic potassium hydroxide or sodium hydroxide. Remember that for the previous reaction for the substitution, we heated with aqueous sodium hydroxide or potassium hydroxide to make the alcohol. But now for the substitution, for the elimination, when we use the OH as a base, we're gonna heat with ethanolic potassium or sodium hydroxide. The mechanism is so easy again. So now this the lone pair of electrons on the OH or the electrons on the OH are going to act as a base now. They're going to attack this hydrogen on the adjacent carbon, and then the bond between the hydrogen carbon is going to break now and go to make a double bond, and then the bromide is going to leave as well. That will give you at the end your alkene. If you want to make the alkene from the alcohol, the mechanism is going to be different. It's called dehydration now, and the reaction conditions is different because you are heating with concentrated sulfuric acid or phosphoric acid. The acid here is going to work as a catalyst. So the first step is not going to have a base, which is going to remove the hydrogen, but rather it's going to be the alcohol acting as a nucleophile, and it's going to attack the proton, which acts as a catalyst here in this part. So this is the arrow go this way, and then you're gonna make the oxygen with a positive charge after you added the hydrogen. Then the bond between the carbon and oxygen will break and goes towards the oxygen, and that will create a carbocation, and then the second hydrogen or the second proton is going to leave to make the double bond at the end. Don't forget that water molecule will be removed as well. Electrophilic addition reactions, we're going to find electrophilic addition reactions with the with alkenes. So alkenes undergo electrophilic addition reaction. This is because the double bond between the two carbons is electron rich, and they act as electrophiles, act as a nucleophile. So they are attacked by electrophiles because this is a nucleophile, basically. So if you have something like hydrogen chloride, the hydrogen will act as an electrophile, and the mechanism of the reaction where the electrons from the double bond will attack the hydrogen, the proton. At the same time, the bond between the hydrogen and chlorine will break. So the hydrogen will be added to one of the two carbon atoms, and that will create a carbocation, and then the chloride that left from the first step is going to attack the carbocation to make the bond. Remember that it's very common in the reaction that they're going to ask you about this reaction with the use of unsymmetric alkenes. Don't forget to refer to the two different carbocations that will be created. One of them is going to be more stable than the other. So primary carbocations are the least stable, followed by secondary carbocation, and then the tertiary carbocations are the most stable carbocations. So when you add the hydrogen to carbon number one, that will create a secondary carbocation, which is more stable. So this is why when the bromine, then a bromide attacks this carbon or this carbocation, that will give you the 2-bromobromine, which is going to be your major product. The other product, which is 1-bromobromane, propane, that comes from the primary carbocation, will be the minor product. Another electrophilic reaction is the addition of bromine. It's the same mechanism, but basically this time, instead of adding two different atoms, you're adding the same atom. So even if you use unsymmetric alkene, you're going to end up with the same product where 2-bromide has been added. Addition of water or hydration is going to follow the same mechanism for the electrophilic addition, like HCl. Now you have an OH and hydrogen, so it's gonna follow the same rule where the carbocation formed the most stable carbocation will give you the major product. You don't need to know the mechanism of the reaction, you only need to know that they use sulfuric acid as a catalyst for this reaction with water. Nucleophilic addition to carbonyl. If you have a carbonyl group which has a carbon with a double bond oxygen, then the type of reaction when they react with a nucleophile, the type of addition is going to be nucleophilic addition because the attacking species is a nucleophile. For the carbon-carbon double bond, the attacking species is an electrophile. Basically, what is added first is an electrophile, but now what is added is the nucleophile. So for this reaction, you can use hydrogen cyanide, but it's very toxic and very difficult to handle. So normally they use sodium cyanide with an acid. So the first step is the addition of the cyanide. So the cyanide is going to be added to this carbon electron deficient carbon, and the double bond between the carbon and oxygen has to break at the same time. That will give you this intermediate, and then you have your acid, you have the hydrogen. The hydrogen will be added to the oxygen to give you the final product. Also, addition of hydride with the hydrogen with a negative charge is going to follow the same mechanism. The product here is going to be a reduction product, so you're going to end up with an alcohol. Addition elimination reactions or mechanism. This is for acyl chloride or anhydride when they react with nucleophiles. The nucleophiles could be alcohols, amines, or water. So the product will depend on what is the nucleophile that has attacked. So as you can see, there are two steps in this mechanism. First one is addition, second one is elimination. So you have the nucleophile first. It's going to attack the carbonyl carbon and the bond here is going to break. That will give you the intermediate. And then the second step is going to be the elimination, where the negative charge on the oxygen or the electrons that move to the oxygen will move back to make the double bond as a carbonyl group again. And then you have the chlorine or the chloride is going to leave now, or this is the elimination step. So at the end, if you the attacking species is methanol, the methanol then is going to have a positive charge here on the oxygen. So the chloride that has been removed will then act as a base in this second last step, where it will take away the proton. Don't forget that the electrons will move from the bond into the oxygen. That will give you the ester as a product. If you use water, you're going to end up with an alcohol. If you use an amine, you're going to end up with an amide. Esterification is the formation of an ester from using an acid and an alcohol. So in the reaction, they could give you any acid with any alcohol and ask you to draw the ester. They're not going to tell you that this is an ester. Remember that this reaction requires a hydrogen catalyst. So in this reaction, if you have a carboxylic acid functional group and then they give you an alcohol with an acid as a catalyst or hydrogen plus, that means a hydrogen an acid catalyst, then you're going to just form the ester. So whatever the carboxylic acid and the alcohol, you just form the ester between these two. Hydrolysis is the formation of alcohols from esters. So hydrolysis is breaking down with water. There are two different types of hydrolysis, and the product will differ depending on the catalyst used. So the first one is the acid catalyzed hydrolysis. So you use water and you use an acid as well, and then the products are going to be the acid and the alcohol. But if it's base catalyzed hydrolysis, where you use something like sodium hydroxide, of course, sodium hydroxide is going to be in aqueous solution, so there will be water as well. So this is going to be hydrolysis, but the products are going to be the sodium salt of your carboxylic acid and the alcohol. If you use potassium hydroxide, it's going to be the potassium salt of the carboxylic acid. Electrophilic substitution to benzene. Benzene behaves differently from the alkenes. They do not undergo nucleophilic substitution, but they undergo electrophilic and they do not undergo addition reactions like alkenes. So they are different. They undergo electrophilic substitution. So we know that benzene ring has this ring of delocalized electrons, so they act as electron-rich source. So they can be attacked by electrophile. The mechanism is going to be exactly the same, whatever the electrophile you're gonna use. So you have your electrophile, which has a positive charge. The attacking bond first, or the first attacking step, or the first step, is that the electron ring inside the benzene is going to attack the electrophile, and that will open that electron ring, or the breaking the aromaticity of your benzene ring. And when you draw this second step, remember that when you draw this curve, this open curve, remember that it's only open next to the carbon where the electrophile was added. So don't make it smaller, or don't make it like an open and including more than one carbon atom. Don't forget the positive charge inside, and then this is very unstable intermediate, so the hydrogen has to leave straight away and giving its electron back inside the ring, and that will give you the substitution product, and of course you're going to have the hydrogen that left. So first one for the electrophilic substitution is the halogenation. For halogenation, you would need a catalyst. So you can use bromine, and then you can use a halogen carrier like iron bromide or ferric bromide, or you could use also aluminum chloride, so that the reaction between iron bromide and bromine will generate the bromide, the PR plus, or the electrophile that's going to be attacking the benzene ring. Friedel-Crafts acylation and alkylation. If you want to add an acyl group or an alkyl group to the benzene ring, then you will need an electrophile that's going to be either an acyl group like CH3, a double bond with a positive charge, or like CH3 with a positive charge. So for the acylation, you're going to start off with acyl chloride, and the catalyst here is going to be aluminum chloride that generates the electrophile, which has a positive charge, and then the electrophile will be attacking the benzene ring in the exact same way and the same mechanism we referred to, and then the chlorine at the end is going to take the hydrogen away or the proton away, which will give its electrons back into the ring to give you the product. If it's going to be alkylation, then you can use alkyl halide, something like methyl chloride or methyl bromide, for example, with the use of the aluminum chloride. That will give you the product as well, but here the attacking species or the electrophile is going to be an alkyl with a positive charge, an alkyl group with a positive charge. Nitration is another type of the electrophilic addition, but now we don't use the halogen carriers like iron bromide or aluminum chloride. Instead, we use a mixture of nitric acid and sulfuric acid. Sulfuric acid here acts just as a catalyst to generate the nitronium ion, which is the attacking species. This is your electrophile. And for this reaction, is the exact same mechanism. We don't need to repeat it. Remember that you need to keep the temperature below 55 degrees in order to get the monosubstituted nitrobenzene, because if the temperature goes beyond 55 degrees, then the nitrobenzene will still going to undergo another substitution to give you the two substituted and 1,3 and the 1,3,5 substituted trinitrobenzene. Reduction, so we can see reduction with of cyanide to make amines. Remember that the cyano group is added to any carbon chain to increase the number of carbon atom in that chain, because cyanide can be added to um, 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 halogen alkane. If you have a halogen alkane, you can substitute the halogen with a cyano group, and then the cyano group can either undergo reduction to give you primary amine, either by the use of sodium borohydride or by the use of hydrogen with a nitrogen catalyst that will give you the primary amine in a reduction, or the cyanide can be hydrolyzed with water to give you carboxylic acid. So if you have something like this one, then when you use water, it's going to be hydrolyzed to give you the carboxylic acid, so COOH here. Remember that to make aromatic amine, you can reduce nitro compounds, and in this case, you need to know the conditions for this reduction. This is by the use of 10 and concentrated hydrogen chloride with reflux that will cause a reduction of the nitro group into primary amine. Phenols. So phenols is a different group of aromatic compound. They are weakly acidic in comparison with carboxylic acid. So they have a pH which is a bit, less than 7, but it's not but it's higher than carboxylic acids. They do not react with weak bases like sodium carbonate, but they react with or can be neutralized with strong bases like sodium hydroxide. The reactions of phenols will increase the electron density inside the benzene ring because they have lone pair of electrons, which can push the electron inside the ring and be part of the delocalization or delocalized electrons. That will make the benzene ring subject to attack by bromine, for example. So if you use bromine water with phenol, that can bromine can undergo or the benzene ring can undergo the electrophilic substitution with bromine, and that will give you 2,4,6 tribromophenols. Reaction with nitric acid as well with nitric acid, that will make the benzene ring more reactive. In this case, you don't need to use conch sulfuric with conch nitric acid. You can simply use dilute nitric acid and the phenol is still going to be nitrated. And it's going to give you a mixture of 2-nitro and 4-nitro products. The directing effect of the substituents on the benzene ring. As you have seen that when we reacted the bromine only went to position 2, 4, and 6 in the benzene ring with the phenol. This is due to what we call the directing effect. So if you have an electron donating group like an OH or NH and nitrogen, both of them have lone pair of electron, they're gonna direct the electrophile to position 2 and 4 of the benzene ring. So you can end up with products that have either one product, 2 or 4, or mixture 2, 4, and 6, or 2 and 6. So any of these three can actually be produced. Remember, the reason is that the lone pair of electrons on the nitrogen or oxygen are delocalized into the benzene ring, and that increases the electron density and make the benzene ring less stable, so it becomes more reactive basically and more susceptible to attack by electrophile. Electron withdrawing groups like nitro group, they will direct the electrophiles to position 3 and 5. This is why when we had nitrobenzene and we said that if we heat it to higher temperature, it's going to give you the 1,3,5 trinitrobenzene. Organic synthesis scheme. You're going to have several organic synthesis schemes in your reaction, and you need to know how to think about these schemes. So how to answer this? First of all, you need to think about the role of your compound and the role of your reagent, whether which one is electrophile, which one is a nucleophile. Look where the change is in the product. For example, here in this reaction in step 1, what happens here is that there is a nitro group here. So this is the electrophilic substitution of or the nitration because this is we substituted the hydrogen with an NO2. As the second step, for example, here you can see that the only change that happened is that the nitro changed into an amine. This is aromatic, so you need also to think about how to make that change. So now to make this, we would need a reducing agent, which is the 10 with the conc HCl. Remember that reactions are always either substitution, addition, or elimination. Even reduction is either an addition or it could be a substitution. You need to think whether your functional group is on an aromatic or aliphatic moiety or aliphatic part. So for example, this one, as you can see, the step 4 here in this reaction, the change that happened on the aliphatic part. This is chlorination. So this is the free radical chlorination to the the methyl group because this is an aliphatic. So here, for example, you use the UV and the chlorine. Again, at the end, you need to think whether your compound is polar or non-polar. So polar ones mean you have a partially positive and partially negative parts, and they can act as either a nucleophile or an electrophile. How to answer something like that? This is from a past exam paper. First of all, you need to think about the role of your reagent and think about look at all the functional group. For example, here you have sodium borohydride. You have something at the beginning with the use of sodium borohydride that gave you 2-hydroxybutanoic acid. So the sodium borohydride, the role of this reagent is that it's a reducing agent, which means we reduced something. When you look at your product, then the only thing that can be a product of reduction is this alcohol, because carboxylic acid comes from oxidation. So the only thing that can happen actually is this alcohol. And we know that sodium borohydride is used to reduce the carbonyl group. So this must have been a carbonyl group. So the only change here is this alcohol is going to change into a carbonyl. So there is a ketone here. So just add the rest of the substituents. And then the next step, now you have two functional group. You need to look about all the functional group and look where the change could happen in your product. So now you have an alcohol and the carboxylic acid. These are the two functional group. And what you added here was an alcohol with sulfuric acid with reflux. So an alcohol will react with which function group? It will react with the carboxylic acid. So that will make an ester with this carboxylic acid. But here, as you can see, they added an acid with sulfuric acid and reflux. So the sulfuric acid is just a catalyst for this reaction. You have the carboxylic acid and it's going to react with an alcohol basically. So now you're going to have the ester but with this alcoholic OH. Finally, this step here, you have a cyano group, which has changed into a carboxylic acid group. To change the cyano into carboxylic, you just need to add water. So just addition of water will make that a change. And the reaction in the exam, they're going to be new reactions you never seen before, and they were going to ask you what would be the product for another reactant. So how to answer this? Start by checking the change in the represented reaction. So this reaction, for example, what happens is that they reacted the alkene with ozone, and then this double bond broke, and then it was replaced with an oxygen double bond or with a carbonyl for both fractions. So what you need to do when they ask you to apply the same here, so I'm just going to break this one, draw the rest of the compound for each of the fragments and or each of the parts, and then I'm going to add the oxygen, replace that with oxygen, so and add extra oxygen. So same number of carbon atoms, 1 2 3, and the other one is same number of carbon atoms, 2 carbon atoms. This one as well, just break this one, and then you're going to draw your product. Remember that because this is a cyclic structure, it's going to be only one product, but instead of having this as a ring, I just going to add a double bond oxygen on both sides here and there. You just apply the same principle in your compound. How to plan a synthetic experiment, how to answer this question. So first of all, you need to do your math in order to calculate the mass needed from the starting chemicals, and that's based on the yield. So usually the question will come that starting from chemical X, you need to plan an experiment to make chemical Y. The chemical Y, they produced like a certain number of grams of the product, and the reaction yield was like 50%, 60%, or whatever they're gonna give you. So you need to do the math in order to calculate how much you're gonna use from the starting material or from the first reactant to end up with that number of grams of your product. To do this, first you have to calculate the theoretical product mass or the maximum mass that can be obtained from your product. This is the mass obtained from the product, the actual mass that was obtained divided by the yield. So when you do this, you're going to end up with the theoretical product mass. And then you need to calculate the number of moles of your product and number of moles based on the theoretical product mass. So basically this is going to be the mass you obtained, and you divide this mass you obtained by the MR of your product. And then this is going to be the same number of moles for the reactants as well, because one reactant was going to give you one product in the reaction. So now we know how many moles we need from the reactant. So we can calculate now the mass of the reactant, the moles of the reactants times the formula mass for the reactant. Don't forget to use your knowledge of the different reactions we just talked about to show the reagents used. Very important to show the reagents and the reaction condition, whether it's going to use reflux or just at room temperature or whatever. If there are any catalysts you're going to use, you have to refer to that as well. And don't forget to run it through your equation. So you have to write a complete equation for the reaction showing the displayed formula of the reactants and the products. And at the end, you can add also how to refer to purifying your product as well. Purifying organic molecule is important as well. So remember that you add water to remove the water-soluble impurities during the washing up step. You add drying agent to remove any excess water, like anhydrous magnesium sulfate. You use separating funnel to remove water-soluble impurities from the products, because the product, if it's a liquid and it's not going to be mixed with water, or if it organic molecules can dissolve in organic solvents which are not mixed with water, so that allows us to separate the two components. Remember that volatile liquids can be purified by distillation, so and if the boiling points of the different products are in close proximity or in a close range, then you use fractional distillation. Remember how to do crystallization for your solid, and then remember that the melting and boiling points can be used as a good indicator for purity, because impurities increase the melting point and decrease boiling point. Polymers is definitely going to be in your exam. So there are two types of polymers. We have the addition polymers, which are for alkenes, just to draw the addition polymer or the monomer. Mostly in the exam, they ask you to draw the monomer or the repeating unit. So you simply arrange your alkene, where you're going to have the double bond here on this line, and then you're going to add all substituents vertically, and then just remove the double bond and draw these two new single bond. This is going to be your repeating unit, whatever is going to be here. So it doesn't really matter what are the different substituents. Condensation polymers comes from or condensation polymerization. It comes either when you react two carboxylic acid or a compound which has two carboxylic acid groups, like X here, and then two carboxylic acid groups, and or it could be an acyl chloride on both sides, like this one, with an alcohol, or it could be the carboxylic acids then with an amine that will end up either making an amide or making an ester. Remember that proteins and DNA are naturally occurring polymers. The chemical test for identification of the function group, this is a table that summarizes everything for you. So remember that bromine water can be used to identify the unsaturated aliphatic compounds. The unsaturated one, by the way, can be either alkene or alkyne, the one with triple bonds as well. It decolorizes the bromine water. Remember that phenols react with bromine water as well, and they can give you white precipitate with the tribromophenol, and it also decolorizes bromine. Potassium dichromate, acidified potassium dichromate, this is an oxidizing agent. It can oxidize primary and secondary alcohol, but not tertiary alcohols, and also it will oxidize the aldehydes, but not the ketones. So they can be positive for aldehydes, primary and secondary alcohols. Tollens test, it's only positive for aldehydes. So this is specific for aldehydes. It gives you a silver mirror. 2,4-DMP, this is used for aldehydes and ketones for the carbonyl group. That gives you a precipitate that varies in color between yellow, orange, or orange-red color, depending on the structure of your carbonyl compound. You can separate that precipitate, and you can compare its melting points with a data book, or a database that can help you to identify the structure of your carbonyl compound. This is positive for both aldehydes and for ketones. And then finally, sodium carbonate. Sodium carbonate gives positive test only with carboxylic acid, so it causes fizzing and then or effervescence, because there are carbon dioxide that has been generated here. So you can test this carbon dioxide with lime water. Isomers, so the Z and E isomers of alkene. So remember that isomers of alkene are only generated when each side of the double bond has two different substituents. If they have similar substituents like two hydrogens, like two methyl group or whatever, then it's not going to be isomers. So if the two groups which have B priority are on the same side, this is going to be the Z isomer, and if they are on opposite sides, it's going to be the E isomer. Remember the S and R optical isomers. These are the optical isomers which rotate a plane polarized light in opposite direction. Remember that these isomers are non-superimposable mirror image to each other. And when they ask you to draw, and definitely in the exam they're going to ask you to draw the isomers of two optically active isomers. In this case, to draw this, you need to draw one of them and then draw the other one as a mirror image for the other one. So first start with drawing this A, and then just for the B, the other isomer or enantiomer. This is going to be the mirror image for the first one. When you draw the 3D structure, you have to use these two wedged bonds. One of them is the solid one and the other one is the dotted one. So remember that you have to use these two. Remember that structure isomers, you will be asked to draw structure isomers for a certain compound, or they're going to ask you there is a structure isomers for something, another compound, and give you some data and ask you to try to find the structure. Remember that, and this is very common in the exam, by the way, remember that amino acids are optically active. They are all have chiral centers because they have this carbon where they have the carboxylic acid group, the amino group, hydrogen, and then the R side chain. The only amino acid which is not optically active is glycine, because glycine, the R group is hydrogen. So optical isomers, they have to have four different substituents on the carbon atom. How to identify how many chiral centers in your compound. The main rule is that it has to be carbon atom. It has to have only single bonds. So a carbon atom with a double bond will never be a chiral center. And it has to have four different substituents. So the four different groups or the four different the four groups or the four substituents on the carbon have to be different. And it can be part of a ring. So for example, here, as you can see, this is not a chiral center because we have two methyl groups here attached to this carbon. This one is a chiral center because there are four different substituents. This is a chiral center as well because we have methyl and ethyl, hydrogen, and then the rest of the molecule. So it's four different. So what if they get you something, a big structure like this one, and ask you to identify how many chiral centers? So let's have a look. So this is a chiral center because it has four different substituents. This is part of the ring. That's absolutely fine. This is another chiral center, and then you have this one, this is 3, and this one, this is 4, this is 1, so 5, and this is 6, and then you have this one 7, and this one as well 8. These are all the chiral center. If you look at each and every one of them, you're going to find that they have four different substituents. This is not chiral at all because it has a double bond, and this is of course not chiral as well